I want to do just a couple more set operations here and just talk about some of the more interesting things that you might run into. Here I've got some sets. I could draw this Venn diagram. I don't think I really need to. But say I wanted to find G complement. Remember, that's just everything in U that's not in G. I can look at these two sets and say, well, 2, it's got 3, it's missing 4, it's got 5, it's got 6, it's missing 7, it's missing 8. Okay, I can find that set without too much trouble. What if instead I wanted to find the complement of the universal set? So from our definition, this is the set of all x such that x is in the universal set and x is not in, or is not a member of, the universal set. Well, when I look at that, I think there better not be any elements that are both members of the universal set and also not members of the universal set. Otherwise, U's probably not a set, right? It needs to be well defined. So that means that the complement of the universal set is the empty set. Similarly, if I have the complement of the empty set, that is, well, the set of all x such that x is an element of the universal set and x is not an element of the empty set. Well, what is in the universal set and not in the empty set? Everything. Because everything's in the universal set, there's nothing in the empty set, so the complement of the empty set is the universal set. All right, a little odd, I admit, but let's look at some more examples. If my set, let's add another set in here and call it I. If the set I was 1, 4, 9, happens to be the set of, oh boy, I can't have 9 in it, because 9's not in the universal set. The set I is the set 1, containing 1 and 4. What is H intersected with I? Well, when I go to look, what do H and I share in common? I find nothing. H and I have no elements in common, so their intersection is the empty set. All right, that doesn't seem too crazy. What if I took G and intersected it with the empty set? Well, that sounds a little strange, but I must be able to do it. They're both sets. I can do these set operations on them. So I want everything that is in both G and the empty set. Well, when I look at the elements of G, 1, is 1 in the empty set? No. Is 3 in the empty set? No. Is 5 in the empty set? No. Is 6 in the empty set? No, I don't think so. The intersection of these two sets must be the empty set, because there's nothing in both G and the empty set. Okay, let's keep going here. See where this takes us. What if I were to take H and union it with the empty set? Well, this means I want everything that's in H, so I'm going to start listing that. 2, 3, 7. And then to that, I want to put in all the elements of the empty set. Well, that did not take very long. I'm already done. This is just 2, 3, 7. Because the empty set doesn't add anything new. H unioned with the empty set is just H, just whatever H had in it. Finally, let's do, what if I were to take G and union it with the universal set? Well, to do that, I would take everything that's in G, 1, 3, 5, 6, and then I need to put in everything that's in the universal set. Well, I need 2 as well. I already have 3. I need 4. I already have 5. I already have 6. I need 7. And I need 8. If you look at this new set we just made, you'll notice, hopefully, this is just the universal set again. So G unioned with universal set is a universal set. And in general, that's true as well.